All right. So welcome everyone. It's it's Tuesday, 4 p.m. here in Warsaw, at least, and we begin our Warsaw University Astronomical Observatory seminar. Today, our guest joins us from the British Isles, from Sheffield, Dr. Stephen Parsons, and I leave the introduction and the chairing of this seminar to Mariusz Gromacki.
Okay. Stephen got his master degree in University of Kent in 2008. After that, he got the PhD from Warwick University under supervision of Professor Tom Marsh, and in 2012 he moved for the postdoctoral fellowship to Universidad de Valparaíso in Chile, where I met him. And he spent there 4 years, and 2017 he back to the UK to University of Sheffield, and currently he got prestigious fellowship, Ernest Rutherford Fellowship. Stephen, floor is yours.
Okay, thank you very much for the invitation. As you can see here, what I'm going to be talking about is post-common envelope binaries. And basically kind of summarizing how these systems are useful for a range of different astronomy. So kind of a summary of what I'm going to be talking about. I'll go through common envelope evolution because it may be a topic that people aren't particularly familiar with. I'll then show you how we can use the binaries that emerge from this common envelope phase to actually constrain observationally the parameters of the common envelope phase. And then looking forward into the future, seeing how these post-common envelope systems will evolve and eventually die. And of course, we believe that most, if not all, thermonuclear supernova must have evolved through at least one phase of common envelope evolution. So I'm going to kind of pay particular attention to that pathway. And after that, I'll focus a bit more on the actual stars within the binaries. So here specifically, I'm talking about white dwarfs. So I'll talk about how we can constrain the structure and composition of white dwarfs using these binaries. And then also the companion star to the white dwarfs, that's usually a low mass star. I'll talk about how we can constrain the properties of them as well. And then finally, I'll end off by talking about the search for planets around these systems, which is a bit of a kind of unusual topic, but you know, there is some evidence that perhaps some of these systems could survive common envelope, which is quite an interesting idea. Okay, so what exactly is common envelope evolution? Well, this idea first comes about when you take a look at the kind of binaries that we see in our galaxy and, in fact, the wider universe. So you've got systems like cataclysmic variables, which are very close binaries, where you have a white dwarf accreting from a main sequence star. You know, these have been known about since the 19th century, at least. You know, at least they're discovered far before then, but that's when they're kind of first characterized. And you've got things like close pairs of white dwarfs and millisecond pulsars. And of course, right now, the big thing is all these sort of gravitational wave events, you know, the binary black holes. And the thing that you may notice in all of these kind of systems is, for starters, we're talking about binaries that are very close, right? So short period systems. And these binaries contain at least one compact object, right? So at least one stellar remnant, a white dwarf, neutron star, black hole, that kind of thing. And so immediately a question kind of arises, you know, if I take this cataclysmic variable system, for example, right? So here we've got, you know, in our kind of generic picture of a cataclysmic variable, we have a white dwarf. So that's the kind of blue dot right in the middle of this big disk of material that's it's accreting from. And then we have this main sequence star, so this red star in this picture, that's filling its Roche lobe, right? So the material right on the inner edge in the L1 Lagrange point, basically the material at this point is feeling a stronger gravitational pull from the white dwarf than from the star it's actually part of. And so this material is overflowing the Roche lobe down towards the white dwarf. And crucially, when we look at these systems in our galaxy, the two stars here are separated by of order a solar radius, right? And that's when the problem starts to arise, because if we look at the white dwarf, obviously the white dwarf wasn't always a white dwarf. And so if you wind the clock back, originally it could have been something about 200 solar radii. And so there's a real kind of mismatch here between the current separation of these stars and how it would have been in the past when we wind the clock back. Now, for those of you with nice high resolution screens, you may just about be able to see a little red dot down the bottom there. If I zoom in on it, that's actually the cataclysmic variable system to scale, right? So this is the kind of difference in scale we're talking about here, right? So it became immediately clear that these binaries cannot possibly have always been this close to each other, right? Some event in the past must have brought them in closer to each other, or it just simply wouldn't have survived. And so that's basically where this idea of common envelope evolution first arose, right? So the idea here is that your original binary is born with a separation of, perhaps an astronomical unit or so. And then the more massive star will eventually evolve off the main sequence, start to expand into a giant. And then if this giant has developed a deep convective envelope by the time that its radius reaches its Roche lobe, when it starts to transfer mass onto its companion, it will become what we'd say dynamically unstable. Basically, what it means is, when you have a convective envelope, if you remove material from a convective envelope, the way that it adjusts to its new lower mass is for the envelope to actually expand, right? But if you're losing mass and then expanding, then that means you're going to fill the Roche lobe even more, which means you're going to transfer even more mass, which makes you expand even more, right? And you can see that this quickly becomes a kind of a runaway process where basically the giant star starts dumping more and more mass onto this kind of poor companion star that simply can't keep up with the amount of material that's getting thrown at it. And so very quickly, this companion star will also fill its Roche lobe. And you end up with this what we call this common envelope, this envelope of material that envelops both stars. Now, of course, this envelope isn't necessarily rotating at the same period as the binary itself, right? Could be rotating a lot slower than the stars. And so effectively, these stars that are embedded in this envelope will feel a kind of headwind, right? They're just trying to kind of plow through this envelope of material. And the effect of that is that they will lose orbital energy, right? Orbital energy will be transferred from the orbit into the envelope, right? And eventually enough energy will be transferred into the envelope that it will be ejected. But of course, at that point, the binary has lost so much orbital energy that it's shrunk down to these much tighter separations. And the crucial thing is that we believe this phase is quite common and can also lead to the generation of many, many exotic binaries that we see in the galaxy and the universe at large, right? So I've mentioned a few of these already, but I've got a very non-exhaustive list here of other types of systems. I will also mention, though, that this is not the only way to make these very short period systems. There are a few other kind of ways of doing it, but we believe that this is the kind of the most major way that this happens, the most common way of creating compact binaries. Okay, so the common envelope phase itself, we actually believe that that is an extremely short process, right? Probably less than 1,000 years, but it could actually be much shorter than that. It could be just a few orbital periods, right? So it could be as little as a few decades. And so you've got the problem when you're trying to simulate this common envelope evolution, that you've got a huge range of length scales we're talking about here, right? So from the very small binaries up to these massive giant stars. And at the same time, you've got these very different time scales as well, right? So you've got these evolutionary time scales of the stars, and then these very, very short dynamical time scales. And the result of that is it's actually extremely difficult to simulate a common envelope event. There have been a few kind of hydro simulations of this stuff that are, they're showing promise, but as yet we can't get a full evolution and manage to get the entire envelope ejected yet. And so for now, we actually use a simpler analytical approach to constrain common envelope evolution. Right, so I mean, they tell you never stick equations in these talks, but given that I'm going to spend the next few minutes talking about this alpha CE parameter, I think it's good to hopefully give you a little bit of context about where this comes from. So the way that, at least one of the ways that common envelope evolution is constrained is using this alpha parameter here, right? So what we're saying here is on the left-hand side, this is the gravitational binding energy of the envelope of the giant star, right? So this is the stuff that makes up the common envelope, and this is the material that we need to eject from the binary in order to emerge from the common envelope, right? So we need to put in this much energy to leave the common envelope. And on the right-hand side, we have the energy that we can pump in, right? So this is the orbital energy of the binary itself, right? So we're changing the orbital energy in order to eject the envelope. And so this alpha parameter here is effectively how efficiently we're able to do that, right? So if during this common envelope phase, we are able to really efficiently use the orbital energy of the binary to eject the envelope, then actually we won't have to use a lot of energy. We won't have to lose a lot of orbital energy in order to eject the envelope, right? We're very efficiently transforming that orbital energy into the envelope, right? So it's going really efficiently in there, and the envelope will disappear very quickly. On the other hand, if this alpha parameter is a very low value, then that means we have to lose so much orbital energy, right? Because it's being very inefficiently transferred into the orbital, into the binding energy of the envelope, right? And so this alpha parameter here is extremely important for dictating basically how rapidly this common envelope event occurs and exactly how much orbital energy is lost. Now, the nice thing is, when you look at the numbers here, on the left-hand side, we've got a few numbers that are basically related to a giant star, right? So, mass of the giant, mass of the envelope, radius of the giant. This lambda parameter here is what we call the structural parameter. So it's basically related to kind of how the material is kind of structured throughout the star. And all of those numbers there you can get from a kind of evolutionary models, right? So if I know the mass of a star and I know what phase of the evolution it's in, then evolutionary models will tell me what mass is in the envelope, what mass is in the core, what the radius is, and what the structural parameter is. Now, the right-hand side, this is basically related to the kind of the changes in the orbit, right? So if I observe a system that has emerged from the common envelope, then I know the masses of the two stars, right? Assuming I can measure that, of course. So M2 would be the mass of the companion. MC is the mass of the core of the giant, but of course that's just the same as the mass of the remnant, right? So a white dwarf in the kind of systems I'm looking at. AF would be the final separation of the binary, which of course I can measure if I catch these things after they've come out the common envelope. And AI is the initial separation of the binary. But of course, if we're assuming that all of this happens really rapidly as soon as the binary comes into contact, then that initial separation is basically the same as the radius of the giant star, right? And so if you make all of these assumptions, then basically, if I observe a binary, I measure the masses and I can determine what that orbit was when it came out of the common envelope. Then I can use evolutionary models, given I've got a core mass, there'll be a range of models of giant stars that have that core mass. There'll be a range of parameters here that will relate to that. And so from this, in theory at least, you can constrain alpha CE from observations of a single object, right? Now, in practice, what happens is that you have your core mass, but there are many models that could have that core mass, right? And so for a single object, you tend to end up with a very wide range of alpha that could have created that. But the hope is if you have a large enough population of these systems, maybe you can start to constrain this alpha parameter here a bit better. So I already kind of briefly mentioned this, but this alpha parameter, it does have a profound impact on the evolution of these systems, right? And can affect the properties of the entire population that emerges from Common Envelope. So here, this is from a simulation of Common Envelope events that is creating white dwarf main sequence binaries afterwards, right? And so here on the left-hand side, this alpha parameter is 1, right? So it's super efficient. We are immediately transferring all of this orbital energy straight into the envelope and ejecting it really quickly. And so what you'll see here, the black point kind of density plot is basically showing you how many systems there are. And so you can see on the left-hand side, there are many, many systems a much longer period, right? Because they, they were able to eject the envelope very quickly. And you also see that there's quite a lot of systems with very low mass white dwarfs. And that's because if you're a low mass white dwarf, that means you entered the common envelope very early on, right? Because the core hasn't been able to grow very much yet. You're only at 0.2 solar masses so far, which means your original binary was very close. But because your common envelope was ejected so efficiently, even though that binary was really close to begin with, it still managed to survive. Now, contrast that with the right-hand side here, where you've got a much lower efficiency, and immediately you'll see all the long period stuff has basically disappeared, right? Because everything is brought in tight because it's so inefficient. But you also see all these very low mass objects have completely disappeared because, like I said, they came into contact when they were still, very early on the giant branch. And so the original binary was much closer. And so these have undergone a common envelope event, but they haven't been able to put enough energy into the envelope before the binary merged. And so basically these systems have merged and they disappear from this sample. Right? So it's very, very different populations we're looking at here. Okay, so that's the kind of theory side of things. And so from an observational side, we say that what we want is a large population of post-common envelope systems in order to try to constrain this alpha parameter here, right? And it turns out that the best population to try and do this with are these detached white dwarf plus main sequence binaries. And here we're talking about low mass, so M dwarf main sequence stars here. And there are a number of reasons why these systems are perfect for this. So for starters, they're extremely numerous. Right? We expect them to be the most common outcome of common envelope evolution. And in fact, we now know of thousands of these things, thanks mainly to the Sloan Digital Sky Survey, which got quite a few spectra of these objects. And you can see why these things are quite easy to identify from their optical spectra, right? Because a white dwarf and an M dwarf are about the same brightness in the optical. And so what you see here, I don't know if you can see my little crosshairs, but in the kind of the right-hand middle plot, at the bluest wavelengths, you see these kind of classic broad Balmer absorption lines from a white dwarf, in a kind of blue continuum. So, there is a white dwarf here. And then at the longer wavelengths, you see these kind of classic asymmetric molecular features and red sloping continuum of an M dwarf, right? So the absolute classic system, very easy to identify from optical spectrum. Obviously there's a bit of diversity with this, depending on how hot or cold your white dwarf is, and if you change the mass and temperature a bit as well of the M dwarf. So you can see, they look a bit different depending on where you are, and some are easier to identify than others. But the other nice thing is, since you see features from both stars in the optical, these are double line systems, which means we can get nice tight parameters for these systems as well. And then if you look at this color plot down in the bottom, a nice quirk of the Sloan survey actually led to us being able to identify thousands of these things. So in this color plot, the main density of points at the bottom, these kind of dark gray ones, these are all main sequence stars. And then the white dwarfs kind of fit right at the end of the sequence, at the kind of bluest end of the sequence. And then all above, all these kind of different colored points, ignore the different colors, and all the open circles, these are all white dwarf main sequence binaries. And the light gray points below, you might just be able to see a kind of cloud of them. These are actually quasars, right? So white dwarf main sequence binaries actually have very similar colors to quasars. And so obviously Sloan did a lot of surveys for quasars, particularly in the early years, and picked up many of these binaries basically as noise, right? So these binaries were their pollution for their samples. But obviously for us, you know, they're great. We're getting all this data for free. And so that's actually, at least in the early days, how a lot of these things were ID'd. Now, of course, once you've identified a white dwarf main sequence system in Sloan, for example, you don't know if that's necessarily a post-common envelope binary, right? It could just be a wide unresolved binary, or maybe just chance alignment on the sky. And so obviously you have to follow these things up, doing a lot of kind of radial velocity studies, which is actually very easy because the periods of these things are only a few hours, right? So you're talking radial velocity amplitudes of hundreds of kilometers a second. So you can actually do it with even relatively low resolution spectrographs. And of course, since the binary is so close, you actually have quite a high probability of eclipsing as well. So a significant number of these post-common envelope binaries are eclipsing. And then, of course, it's very easy to measure periods. And they are, you know, the ultimate systems for constraining the parameters, as you'll see later on. Okay, so now we've built up a large population of these white dwarf and M dwarf binaries. You know, we spent years and years measuring all the radial velocities for these systems. You can fit the spectra, the optical spectra, to try to determine what the mass is, pardon me, of the two stars are. And of course, you measure the periods, etc. And you end up with this period distribution you can see up here in the top right. Right, so it peaks at a period of kind of around 8 hours or so. So most systems have periods around 8 hours, right down to you know, the shortest period end, you know, an hour or so, the most extreme. And you have this tail off to longer periods, longest period system about 10 days. But then you see absolutely nothing beyond that, right? So there's no systems with periods of weeks or months. And the thing is, we do actually have the detection. Sorry, we have sampling that could have detected that, right? So this line above the period distribution is basically a detection probability. And you can see, obviously, it drops as you go to longer periods, but it doesn't drop to zero. So if these things do exist at periods of weeks or months, we should have detected them. So the fact that we didn't means that they simply don't exist, right? So all these systems have very short periods. And so that should immediately get you thinking back to what I was talking about a few minutes ago in terms of this alpha parameter, right? You know, if this alpha parameter is low, that means everything gets brought in really tight orbits. And so you can see here on this plot at the bottom, these are the same two plots I showed earlier, but now with the actual observed periods and masses overplotted. And you can see that the low alpha is a much better fit to the data than the high alpha parameter here, right? And so this is just one of these words. There have been many other papers that have analyzed this sample, and they've all come to the exact same conclusion, that basically for these white dwarf, M dwarf binaries, this alpha CE is a very low number, somewhere between 0.2 and 0.3. And so this means that everything should emerge from the common envelope at very small separations, which, you know, is obviously very interesting then for talking about how these things could evolve in the future. But of course, this conclusion is only based on white dwarfs with low mass main sequence binaries, right? These M dwarfs. And when we're talking about these low mass stars, we're talking about systems that are basically going to go on to become cataclysmic variables, right? That all the masses here are too low for them to be thermonuclear supernova or anything like that, right? So if we want to start talking about supernova and things like that, then we need to go to higher mass main sequence stars and see if this alpha parameter is still the same. So that's what I started doing a few years ago, but it gets a lot trickier when you do that, right? So again, here on the left-hand side, here's a white dwarf with a low mass M dwarf companion. And as I showed earlier, right, you can see the white dwarf features in the blue and the M dwarf features in the red. This star on the right is the exact same white dwarf, but now with a solar type companion next to it, right? And now you suddenly see absolutely nothing of the white dwarf. Right, anyone who can see white dwarf features in that spectrum is got much better eyes than I do. Right, I mean, the white dwarf here is literally contributing much less than 1% of the flux. Right, I mean, look at the numbers on the y-axis here. Right, so basically what this means is, you know, from an optical spectrum alone, it's totally impossible to identify these systems. So what you have to do instead, you have to go to the ultraviolet. Right, so while the white dwarf is totally outshone in the optical in these systems, when you go to the ultraviolet, because these white dwarfs are so much hotter than their main sequence stars, right, they still have temperatures of tens of thousands of degrees compared to, you know, 5,000–6,000 Kelvin main sequence star, then the white dwarf will still dominate in the ultraviolet. And what you'll see when you look at the spectral energy distribution of these systems is it'll look mostly like a main sequence star, but you'll get this little kind of excess flux at ultraviolet wavelengths. And so, in other words, what you see is they have very blue UV colors compared to the bulk of main sequence stars, right? So this plot on the right here shows that most main sequence stars, they kind of sit up in the top right hand corner here, right? So they're kind of very red objects. And then you stick a white dwarf next to these things and that will pull them to the blue. And so we said all these things, you know, all these red dots over here, we would call candidate white dwarf main sequence binaries here. But now we're talking about solar type main sequence stars as opposed to M dwarfs. So of course that's a nice idea, but how do you actually prove that there is a white dwarf next to this thing that's actually causing the UV excess? Well, the easiest way is just to get a spectrum in the ultraviolet. I say easiest, you still have to use Hubble, which is tough to get time on. But we did manage to get some time here. We've observed more than a dozen systems now, and absolutely every single one has shown the presence of a white dwarf so far, right? So here on the left, I've shown some spectra here, and you see this classic, very broad Lyman alpha absorption line, right? Huge amounts of pressure broadening in the spectra of white dwarfs. And so, you know, every single one of these systems definitely has a white dwarf that is responsible for these UV excesses, which is great. So we really have uncovered this population of higher mass binaries here. And so basically we spent the last few years trying to get, you know, the parameters of these systems, measuring orbital periods, masses, etc. And so I've kind of summarized everything in this little picture here. So down at the bottom here, the kind of the lowest mass stars, here's SDSS sample of white dwarf, M dwarf binaries you see sitting down the bottom here. Then there's a few kind of historical systems here in triangles. And then these stars here, these are our systems that we have got the periods of so far. So unfortunately, there's not very many. We only have 4 systems where we've measured periods so far, unfortunately. But these are tough systems to crack. And then actually, so what you'll see above these systems here are what we call these ELCVN or thermally bloated white dwarf binaries. So these systems here, they have very low mass white dwarfs here. We'll talk about 0.2 or maybe even less than 0.2 solar masses. We believe these systems here are actually not post-common envelope systems. Right? We expect that they have gone through stable mass transfer as opposed to common envelope. You see the two populations do actually overlap somewhat here, although the big difference is the white dwarf mass, right? So the kind of systems we're looking at have kind of fairly standard white dwarf masses, while these things have very low mass white dwarfs. And interestingly, there's now this growing population of systems at much longer periods, right? Several hundred days. Now, the interesting thing here is that clearly these systems are close enough that they should have interacted. But the problem is if you assume that they went through a common envelope phase, then it turns out you need alpha greater than 1, which obviously isn't particularly physical, right? That means we needed to put in more energy than, you know, basically we needed an efficiency greater than 1. And so there's these ideas that maybe you can use extra energy from hydrogen recombination, all this kind of stuff, which is kind of a bit uncertain, to be honest. Or the alternative is perhaps these longer period systems actually had some kind of phase of stable but non-conservative mass transfer, So maybe you generated jets or something like that to take away the mass. But it's interesting that there does seem to be a lot more diversity as you go up to these higher masses. And of course, one interesting thing is, as I mentioned, these white dwarf, M dwarf systems are all eventually going to become cataclysmic variables. When you look at these higher masses, we've got our shorter period systems here, which are probably going to come into contact before the main sequence star has a chance to fully evolve, right? And so they can become what we call these super soft X-ray source systems, where effectively the mass transfer rate of material onto the white dwarf is high enough that you can actually stably burn the material when it hits the white dwarf. And so you don't end up with like nova explosions that you get in cataclysmic variables. And so in these systems, the white dwarf can potentially grow in mass. And so these could be, for example, single degenerate progenitors for supernova 1A. And on the other extreme, you have these much wider binaries that won't come into contact again until the other main sequence star evolves. Right, and they'll undergo a common envelope and end up as tight white dwarf pairs. And so these could end up being double white dwarf progenitors. So you can see this population of systems in principle can sample multiple pathways here. But the problem is, unfortunately, the number of systems is still too low at the moment, right? So we don't know, for example, at the moment, if there's a continuous distribution of systems between these two, or if we are seeing two discrete populations of shorter period systems that have undergone this common envelope, again with this very low efficiency, and then a wider period sample that underwent a slightly different evolution. So this is still very much work in progress. Okay, good. So that kind of brings me to the end of the first section. And so now I want to actually start talking about the stars themselves in these binaries. From now on, basically, I'm going to be talking about systems that are eclipsing. Right. So as I mentioned, these systems are close enough that they actually have a very high probability of eclipsing. And the really nice thing here is because the white dwarf is such a small object, right, it's only about the size of the Earth compared to even an M dwarf that's at least a Jupiter size. You end up with these light curves with very sharp eclipses. Right, these contact points are very, very sharp. And that allows us to measure extremely precise radii for these stars, which we can then combine with the spectroscopic data to get masses as well. But of course, the flip side of this, it means you do need to observe these things very, very rapidly. Right, so these this ingress and egress here, they typically can take less than a minute, right, from the start to the end of the ingress. And the total eclipse width can be as short as 5 minutes up to maybe an hour in some of the longest period ones. And so you need to get kind of high speed photometry, right? And so that's where the group here at Sheffield really excels, right? We build these high speed cameras. It's got things like ultracam and hypercam, which are these kind of rapid frame transfer cameras. We can take in principle 1,000 frames a second with hypercam. Unfortunately, I don't have enough time to kind of go into exactly how these cameras work, but if you're interested in that kind of stuff, feel free to ask at the end. Okay, so good. So we've got these really nice light curves, and then I got this program to get a lot of VLT time with X-shooter to follow these things up spectroscopically, and so I've got all these radial velocities of these things, and so I've got about 25 systems in total where we were able to measure really, really precise masses and radii for both stars in the binaries. Right, and so most of these things are white dwarfs with M dwarfs. But there was also a couple of white dwarfs with brown dwarf companions, and even a couple of double white dwarf binaries. And so the idea here is then to try and test the internal composition of white dwarfs, right? And so why do we care about that? Well, our kind of canonical picture of what a white dwarf is probably the middle panel here, right? So you have this big inert core of carbon and oxygen, surrounded by a layer of helium, and then surrounded by a layer of hydrogen. Right, so it's this classic kind of picture of if you have a high gravity object, all the heavy stuff sinks to the middle, all the light stuff ends up on top, and that's what we think the bulk of white dwarfs look like, right? But you can have these odd systems if you go down to very low masses, right, less than about half a solar mass white dwarf. Then what that actually means is the white dwarf never managed to reached the AGB, right? Its evolution was cut off while it was still on the red giant branch before it got to the asymptotic giant branch. And so before it managed to start core helium burning, in which case then you literally just have a big ball of helium with some hydrogen at the surface. You know, it's still kind of an inert ball. And then at the other end, if you manage to evolve, if your original star was pretty massive and you manage to evolve very far along the giant branch, then you can actually start to burn some of this carbon and oxygen into neon, magnesium, etc., before you eventually die, right? So these are systems that maybe just avoided undergoing core collapse supernova, right? And so we have this kind of changing core composition that happens around a solar mass. And the really interesting thing here is that these carbon oxygen core white dwarfs, these are the kind of white dwarfs you expect to explode if you take them up to near the Chandrasekhar limit, right? Because a thermonuclear explosion isn't actually the thing exceeding the Chandrasekhar limit, right? The thermonuclear explosion is the carbon detonating in the white dwarf, right? And so these higher mass ones with these oxygen neon magnesium cores, because they have so little carbon, they won't actually explode as a thermonuclear supernova if you take them up to the Chandrasekhar limit. Instead, what we believe they do, they have this kind of accretion-induced collapse that basically they'll collapse down to a neutron star with perhaps no obvious outward sign that they had done so. Now, the interesting thing is that when you look at the masses and radii of these white dwarfs, there is a subtle change in radius when you change core composition, right? As you go to these cores with kind of higher mass elements in them, they're actually smaller, right? So if you can measure the radius and the mass of your white dwarf to a high enough precision, you can actually distinguish between these core compositions. So that's what we did with this sample here, right? So I was able to kind of measure masses and radii to a couple of % precision. In the best cases, we're measuring the radii of white dwarfs, 100 parsecs away to better than 50 kilometers, which still blows my mind. It's just kind of how powerful these eclipses are. And it is good enough to distinguish between these models, right? So here on this plot, unfortunately, we had nothing high mass. So we weren't able to do anything like what I was just outlining with this kind of Chandrasekhar stuff. But what we did see is when you go below half a solar mass, if you compare your measured radius to models, if you use carbon oxygen models, so here they'd be the black dots, you can see all your points kind of sit a bit high, right? So your measured radius is a bit too large compared to the model radius. However, if you take the helium core models and use those model radii, they're completely consistent with the measured radius, right? So we expected this to happen below half solar mass, but this was the first time we'd ever got direct evidence that the internal composition of white dwarfs do indeed change below half solar mass. Now, of course, focus there on the white dwarfs, but if you want to get these white dwarf parameters, you actually get the parameters for the main sequence star companion for free. So you may as well look at them as well, right? And here we're talking about these low mass M dwarf stars, and people are quite interested in these stars for the search of planets around stars, right? Because if you go to a low mass star, then it's easier to detect lower mass planets around them, Earth-like planets, etc. Any transits will be deeper and easier to detect. And ultimately, all those planets you detect around M dwarfs are only as well characterized as the M dwarfs themselves. And so we can use our M dwarfs in our binaries to maybe say something about how these M dwarfs are structured. So you do the same thing here, and the situation here is a bit trickier, right? So the systems that I added here are all these red points, right? These are the M dwarfs in these binaries. And the first thing you should notice is all these other methods, they're either isolated M dwarfs or M dwarfs in binaries with other M dwarfs or higher mass main sequence stars. And what you can see here is there's basically no obvious difference between the ones in the post-common envelope systems compared to all these other systems, right? So the first thing we noticed is that the common envelope phase itself is not really having a large effect on these M dwarf stars, right? They're mostly unscathed from this evolution. But what you can also see is that yeah, some of these things are consistent with evolutionary models, but a lot of them are a bit too large and there's no obvious reason why. And so we looked into different properties, you know, could this be something to do with how rapidly these stars are rotating, or could it be something to do with metallicity or age or things like that? And nothing seemed to really correlate very strongly. And so it really is quite uncertain exactly where this large scatter comes from. But basically, your star could be up to 10% larger than evolutionary models predict for these low mass stars. And really, there's no obvious way to explain how to do that or to correct for this method without directly measuring the radius, which obviously has some quite serious implications for exoplanet studies. Okay, so speaking of exoplanet studies, I'm going to now finish off by talking about the search for planets around these systems, right, which may seem like a rather strange concept, trying to search for planets around these binaries. But for starters, the eclipsing systems, at least, they give us a new technique to search for planets around these binaries that aren't usually accessible for most objects. And also, you know, there was some really interesting evidence a few years ago that seemed to imply that perhaps planets could be quite common around these systems, and that actually, you know, perhaps even the common envelope phase itself could produce planets, right? It could even be able to make planets out of the common envelope material, which was some kind of interesting ideas. And so we wanted to look at this and see, you know, how reliable is this evidence for planets around these things. Now, of course, we actually have quite a lot of evidence now for planetary systems around isolated white dwarfs. Right, so, you know, the last few years, there have been a lot of results about these so-called metal polluted white dwarfs. Right, so I mentioned that, you know, because of their high gravities, basically all the heavy metals get sucked to the middle of white dwarfs, and all you should ever see at the surface is hydrogen. But actually, there's quite a few white dwarfs now. If you take a spectrum of them, you see all these metal lines in their atmospheres. Basically, it turns out that this must be kind of rocky planetary material that's, you know, falling onto the white dwarf. And that was proved a few years ago by this system WD 1145, where if you looked at the Kepler light curve of this system, you saw these dips. And it turned out these are basically big clouds of dust and gas from you know, some kind of rocky object that's breaking apart, and all this stuff is actually passing between us and the white dwarf. So we can see this thing kind of breaking apart in real time. And then, of course, the real evidence came last year with this system WD 1856, and this is a planet that is transiting a white dwarf, right? So this is a planetary system that has definitely survived the death of its parent star, right, and gone on to survive around this white dwarf. Now, interestingly, this particular planet has an orbital period of about 1.5 days, so it's incredibly close. And actually, the same kind of arguments that I had earlier on about how these original binaries can't be that close also go for this planet. They say it cannot originally have been at that separation. And so there are a number of different theories as to how this planet could have got in close. You know, it could be scattered, or perhaps some kind of three-body interaction. But one possibility is actually the planet itself could have entered a common envelope phase and survived. It's one possibility. Okay, so we know that planets can survive stellar evolution and the death of their star. And at the same time, we know that there is a growing population of planets around binaries, right? So here I'm just talking about normal main sequence binaries, right? So a number of these things have now been discovered in, you know, things like Kepler and TESS, where you see them transiting both stars. And so if you say, okay, we've got planets around binaries and we've got planets around white dwarfs, can we have planets around white dwarf binaries? And as I said, this interesting idea of if you undergo a common envelope, does that help or hinder your ability to either maintain a planetary system or perhaps even generate one? Now, the nice thing with these eclipsing systems is because the eclipses are so sharp, as I showed you earlier, you know, they're really kind of less than a minute or so on this ingress and egress of the eclipses. That means if you can observe them fast enough, so again with these high-speed cameras we have, you can actually measure the arrival time of the eclipse extremely precisely. Right? So in the best cases, we can actually measure the central, the arrival time of that eclipse to about 100th of a second. And this opens up the possibility of trying to detect planets through eclipse timing variations, right? So you see here, this is the kind of archetypal system here, V471 Tau. So this is a white dwarf with a K-star binary here, actually. And you can see that the eclipses start arriving earlier and earlier and earlier, and then somewhere around 1990, they flip around and then start arriving later and later and later. And so the idea here is that you've got your central binary here, right, so composed of your red and blue star, and the entire system is being orbited by a circumbinary planet, right? And then the central binary and the planet, all three objects are actually orbiting the common center of mass of the entire system. And so at certain times in the orbit, the binary system itself will be closer or further away from the Earth. And so there'll be a subtle difference in the light travel time taken for the actual light from the binary to reach us here on Earth, which could cause these eclipse timing variations. Now, one of the most convincing cases for there being planets around these systems via this technique is a system called Nsir. And this was modeled back in 2010 originally by a combination of two planets that was actually locked in a 2-to-1 kind of resonance. Right, so this is the model shown at the bottom here. And this particular system has many, many observations going back quite a long time. So this model was actually quite well constrained. And we could rule out many other explanations for how these timing variations could come about, right? So we could rule out anything to do with activity from the M star or star spots or apsidal motion, things like that. Or we could rule out all these possibilities. And the really interesting thing about this system is its predictive power as well. Right? The model fitted to these eclipse times appears to have some predictive power. So here I'm showing a little zoom in on some of the eclipse arrival times for this system, and I've left the very end here blank. And so I just want you to kind of look at the kind of general trend of these times and try to kind of guess where you think these things would go in the last few epochs. Right, and so that's what the model predicts they should do. Right, the model says actually this eclipse arrival time should really jump up. They should start arriving later and later and later. And that's exactly what they times did, amazingly. Right, so this model predicted the eclipses should start arriving late, and they did. And so if you actually look at the full data set here, you can see kind of where this upturn comes from, right? So it's basically, we're at the minimum of this point down here. And so there were some points further back that kind of constrained this turnaround. And so you can see ever since then, it's been kind of mostly on track with the model. Although you then also need to include an additional term, and that's where things start getting a bit dodgy, saying, if you just have to keep adding in more and more components, at what point do you say, okay, this is just stupid? Flip side of that, though, is that actually turns out when you look in Gaia at Nsir, it actually has a common proper motion companion, amazingly. So Nsir is actually a triple system. And its companion is quite a low mass star. And in principle, that companion object could be responsible for this very long period trend here, which is quite interesting, because if you can say, okay, I've actually observed an object here where I can relate a timing variation to, then maybe that does lend some support to these underlying variations being from planets. However, when you look at other systems, it gets a lot messier. So here on the left-hand side, this is a system we actually observed with VLT sphere, so this high contrast imaging to try and detect the object that was causing the timing variations here. And so in this case, actually, we thought the companion should be a brown dwarf. And so it should actually be bright enough to be detected, but we did not detect it. So basically that system there, we can rule out the circumbinary object that's causing the timing variations there. And then on the right-hand side, this system here, QS-Ver, The timing variations for this one are so extreme and so sharp that it's just impossible to fit these timing variations with the stable orbits of planets, right? The only way to fit these timing variations is to have planets either moving in different directions or orbits crossing. It's just completely dynamically unstable. So clearly there are timing variations in these systems that can't be explained by planets. And it's still very unclear exactly what it is that's causing these timing variations, and whether or not it's the case that even for systems like Nsir that look very convincing, actually maybe it isn't planets. So I'm still pretty skeptical about whether or not there are planets around any of these systems. Okay, so that brings me to the end. I think pretty much on time there. So I guess I'll just leave my summary stuff here up at the end and ask for any questions. So thanks.
Thank you very much. Any questions? Please raise your hand. Okay, Tomek, please ask.
Hello, everyone. Hey, thanks for the great talk. Did I understand correctly that you were able to identify post-common envelope systems that went through the common envelope on the RGB, not on the AGB phase?
Yes, exactly. So essentially, if you see any system with a white dwarf with a mass less than about 0.5 solar masses, it's almost certain that that has to have undergone a common envelope on the RGB. And the fact that we were also able to confirm that these things have helium cores means that these, they never got to the point where they started core helium burning. Right? So they were never horizontal branch stars. They never got to the AGB.
So do you know what fraction of the post-common envelope systems they constitute?
It's actually quite a significant fraction. I don't know the number off the top of my head, but I'd say perhaps somewhere of the order of a third or so, at least, have helium core white dwarfs.
All right. Thank you very much.
Okay, Tomek, could you unraise your hand? Okay, more question? So I have the question. Can we expect something like formation the planetary planet brown dwarf directly from the common envelope product? I mean that the part of the envelope is ejected, and what is left is what is left is the piece of the core which has the mass of the brown dwarf. Could we expect such scenario?
So a few years back, that was actually what everyone thought, because when you look at all these eclipsing systems, basically all of them show timing variations at some level or another. And so you have two explanations there. Either none of them have planets and it's some other mechanism that's generating these timing variations, or they all have planets. Right? And if they all have planets, then that implies that it's something about common envelope evolution itself that is responsible for where all these planets come from. And if you look at Nsir, for example, those planets, where they are in their current orbits, if they do exist, they're in a location that they couldn't possibly have survived if they were there originally before the common envelope. So the idea there would be, yes, that these planets would actually form out of the common envelope material itself. And that is, of course, something you could potentially prove, especially with a system like Nsir, because Nsir is a very young system. It's literally just emerged from common envelope. And so if you've just formed your planet, then it's going to be a lot hotter and brighter than if it formed originally with the binary, right? So if you could directly image it, then you would be able to say for sure if that thing formed out the common envelope or not. So, and of course, the original planets found around pulsars, there's quite a lot of evidence that at least some of them may have actually been formed from the ejector of the supernova. So I don't think it's necessarily a crazy idea to think that planets could form out of this stuff. But as I said, I am still very skeptical as to whether these timing variations are actually caused by planets. My suspicion is that they are not.
Okay, So, and my second question is regards, okay, maybe first Łukasz.
I'm just wondering whether how useful Gaia astrometric measurements could be for detection of binaries with white dwarfs, and I mean not only the current data which do not include any binary motion, but in general the astrometric signatures of those systems.
Yeah, well, when we talk about these planetary stuff, actually, it could be quite interesting for that. If I have a known system, I have a planet around it. In principle, when we get the final astrometric data, the final data release, you may be able to tell if there's a circumbinary object around that binary, at least for some of the closest by objects. In terms of actually detecting systems, I suspect for these post-common envelope systems, if we believe this alpha parameter is this low for all binaries that undergo a common envelope, at least with a white dwarf, then they're all going to have these periods of a few days at most, and they're simply too tight to ever really be picked up by Gaia. But if you've got this population of systems at a few hundred days, then yeah, there's a good chance at least a few of them, if they're close enough, should be picked up. And actually, that's almost certainly the easiest way to find them in the end, right? Because measuring periods of that kind of length is very tricky from the ground. Most of those systems are actually found in Kepler as self-lensing binaries, right? A really odd thing where you've kind of perfectly aligned with the Earth, and as the white dwarf passes in front of the main sequence star, it lenses the Earth, so you get a kind of anti-eclipse.
Well, you mentioned that in Kepler they're being thought. I only heard about one. Were there more than one?
Yes, yeah, there were actually. So
wow.
I think there's 5.
Wow.
Yeah, amazing, because actually the probability of it is quite low.
Exactly.
There's only a very narrow range of periods where you even get efficient lensing. So yeah, quite remarkable that so many were found.
Cool. Okay.
It does imply that maybe they're quite common.
Okay, thank you.
Okay, and the second question is about the neutron stars, which is formed from the oxygen magnesium white dwarfs. So we expect some kind of the explosion during the collapse?
I think most people would say probably not. And in fact, you may not even see any kind of transient when it occurs. It may be the thing just collapses down. But I think the most models seem to predict that maybe you would get a very brief low luminosity transient. That is probably something that's quite tricky to pick up, to be honest. As far as I know, we've never detected anything consistent with that. But no, you shouldn't get any kind of explosion, really.
And do we expect also some kind of the structure difference between the white dwarf neutron star product between the neutron star produced during the supernovae collapse?
Gosh, it's a tricky one. I don't think so. I mean, fundamentally, they would still be supported by the same, physics, right? So, still this kind of, neutron degeneracy pressure, effectively. So, I think fundamentally it would still have mostly the same structure. Yeah, I think it'd be difficult to tell the difference between the two. Obviously, it'd be something that's right at the Chandrasekhar limit, right? So, perhaps that would be a bit of a smoking gun, right? If you measured a neutron star with a mass exactly at the Chandrasekhar limit, for example.
Okay, thanks. So, there are other questions? Okay, I don't see more questions. So let's thanks again. Thank you, Stephen.
Thank you, Stephen, and thank you, Mariusz, for leading this seminar. And thank you all for joining. And see you next week. Please join us on Zoom or YouTube channel where you can see. You can even subscribe to our channel. Thank you and goodbye.
Thank you very much for a great talk, Stephen.